thing is a proof by mathematical induction. To do a proof by mathematical induction is fairly simple. It says proof by mathematical induction that Sn is equal to that thing on the right hand side. So let's write out what Sn is. It says Sn is equal to 1 plus a half plus 1 over 2 square plus 1 over 2 cube, and it continue to be plus 1 over 2 to the n minus 1. And we need to show that this is equal to 2 minus 1 over 2 to the n minus 1. So to do this, this is just mathematical proof. All right, so to do this now, all we're required to do is first and foremost, I'm going to rewrite this Sn here as I'm going to rewrite Sn as Sn is equal to the summation from Sn look like the summation from, all right, I don't want to use Sn. It's a sum from r equal 1 to n of 1 over 2 to the r minus 1. So we need to show that the summation of this is equal to 2 minus 1 over 2 to the n minus 1. So to do proof by induction, we first start from case number 1. Case number 1, this is when we let n equal 1. When n equal 1, what are we going to get? We're going to get that Sn when n equal 1, we're getting Sn is equal to, n is equal to 1, we get 2 over 1 minus 1 is 0. So you get Sn is 1. And let's check it on the right hand side. It is 2 minus 1 over 2 to the 0. 2 to the 0 is 1, which is 1. So yep, the equal on both sides, and so S1 is true. So we can say S1 is true. Since S1 is true, now let's assume that Sk is true. So step 2 for n equal k. For n is equal to k, for n is equal to k, we're going to get that Sk is equal to the sum from r equal 1, sum from r equal 1 to k. So getting Sk is the sum from r equal 1 to k of 1 over 2 to the r minus 1. And that is going to be equal to 2 minus 1 over 2 to the, replace n with k, so it's 2 to the k minus 1. That's for n equal k. And the only thing is, for n equal k, we'll assume this is true. Assume it is true. So you assume it is true. So let's look at the proof now for n equal to k plus 1 to see if it will work out. All right, so let's make some space. We'll do the proof in a box right here. Let's do it in this space right here. Let's do it in another color too as well. So for n equal k, step 3, for n equal k plus 1, for n is equal to k plus 1, what we're going to be getting is Sk plus 1 is equal to the sum from 1 to k. It's equal to the sum from 1 to k, which is Sk plus the k plus 1th term. The k plus 1th term is going to be replace r with k plus 1. So it's plus the k plus 1 term, which is 1 over 2 to the k plus 1 minus 1. That's the k plus 1 term. So again, sk plus 1 is going to be equal to sk, which is 2 minus 1 over 2 to the k minus 1 plus 1 over 2 to the k. Why is it not typing? Not freezing right now. Plus 1 over 2 to the k. All right, so now let's see how we're going to separate this now. Now, of course, we want to show that it's going to work out to be 2 minus 1 over 2 to the k. All right, that's what we want it work out to be. So all we need to do is add these two. All right, we just need to add these two. In order to add these two, all I'm going to do is, instead of writing 2 to the k minus 1, 2 to the k minus 1, this can be broken up as, we can break up this as come on, stop. All right, so as I was saying now, finally it stopped freezing. This can be written as, instead of saying 2 to the k minus 1, it's 2 to the k times 2 to the minus 1. All right, that's how we can write it. So this is now actually equal to, now these two, they really and truly have a common denominator. Now 1 over 2 to the minus 1, 1 over 2 to the minus 1, what is that? 1 over 2 to the minus 1 is 2. So this is really now 2 minus 2 over 2 to the k, 2 over 2 minus 2 to the k, plus 1 over 2 to the k. Plus 1 over 2 to the k. Now 2 minus 2 to the k plus 1 over 2 to the k, that's going to work out to be now minus 2 over 2 to the k plus 1 over 2 to the k. These two part together, when you add them, becomes minus 1 over 2 to the k. But look. 1 over 2 to the k, we can rewrite that then now as that sk plus 1 work out to be equal to 2 minus 1 over 2 to the k plus 1 minus 1. All right, nice and easy. And so now we've proven it. Now it's proven. Nice. Now that it's proven, so we can say hence sk plus 1 is true, or hence n is equal to k plus 1 is true if n equal k is true. Nice. Now, anytime you finish mathematical induction, you don't just done there. So remember that you have to always trying to extend it. Yeah, this is fine. Anytime you finish, you have to always give a conclusion. So your conclusion is hence by mathematical induction, the statement Sn, so the statement Sn is true for all n. So it is true Sn is true for all n. For all n a element of natural numbers. Soft. Now we can go to part 2. It says hence or otherwise find the limit of Sn. So I'm going to go with hence. Find the limit. So it says hence. So the limit as n goes to infinity of Sn. If we're going to find this limit of Sn, then we just found that Sn was equal to a specific formula. And so the limit as n goes to infinity of Sn is actually the limit as n goes to infinity of 2 minus 1 over 2 to the k, 2 to the n minus 1. Now, if you're to plug in infinity in here, what you're going to get is the limit as n approaches 2 is 2. So this becomes 2 minus 1 over, if you plug in n as infinity, this is really 2 to the infinity. 1 over 2 to infinity is approximately 0. So this is approximately 0. So the limit is just equal to 2 minus 0. And so the limit is 2. Easy marks. Soft. Part B says,